All right, well, thank you, and great to be here. I'm Matt Forrest. I head up our solutions engineering practice at CARTO. If you don't know who we are a spatial analytics platform. I'm based out of New York City, but our team's based worldwide in lots of different areas through Europe as well as the Americas. So, wait for the slides to come up. Before we do that, I do generally like to do a quick survey just to see who's familiar with these types of terms. So if you do know these things, just raise your hand so I get a sense for the audience. If you've heard of GIS, spatial SQL, geospatial analytics. Okay, so all right, so you guys know what we're talking about. Good. So today we're talking about cloud-native spatial analysis, and that's something we do at CARTO. CARTO's been sort of a cloud platform since our inception, and that's really what we've done. Now, the other quiz component for today is, can anyone actually identify what this map is? Any takers? All right, so I will tell you, this is a very famous map if you're familiar with geography, history, things like that. It's actually the John Snow cholera outbreak map from London. So this was someone who actually went out and there's a cholera outbreak in this neighborhood in London and they couldn't figure out why that was happening. So what he did quite intuitively was actually go out and find which homes or houses had someone who actually had cholera. And you can't really see it on this map, but if you go, there's actually a water faucet in the area, water pump, that actually was causing this outbreak. And he was able to figure that out by mapping who actually had cholera in the area. And if you go to London today, you can still see said water pump, and there's actually a pub you can go in called the John Snow pub if you actually want to check that out for geo nerds like myself. That's a pretty interesting thing. So that was sort of the birth of geospatial analytics. And of course, when we're talking about this is pretty small data at the time, but we had to manually go out and collect all this data. What's happening now, and of course this is probably problems you face, is that data is being produced at a much more massive scale. So if you're working with connected devices, you're getting lat long sent to your database or data warehouse on a pretty consistent basis. You might be collecting that data from IoT connected devices. You might be collecting that in the form of purchases or collecting that from marketing campaigns. So there's lots of data coming in at a regular basis. Now, you're probably already working with this data. So this is a small sample of some data around here. Some of it's real, like our address here at the hotel where we are currently, our postal code, our latitude, longitude, and 3520, which is actually the code for the dissemination area that we're currently in. But other ones you might not know is this string that's below there, which we'll talk about in a minute. It's called an H3 cell, and it's pretty important to some of the things we're doing, as well as this thing called a polygon. That's a fake one, but if you are familiar with GIS, you know the structure of a polygon. It's a boundary or a shape like a box or any sort of shape that you might have. So you might already have that data, but how do we really make this useful at scale? And this is a pretty famous data set in the data science, kind of the Kaggle competition space. It's the New York City taxis data set. There's actually a solutions engineer from CARTO who previously worked there that actually got access to this data. He sent in a FOIL request to the city, and a few months later, they told him to come down with a hard drive and actually get all that data from the city. And that's how we have this data today, if that's just an interesting side story. But if you ever touch that data set, it's something like 300 plus million rows of data of every Uber taxi trip. Has the fare information, the tip, the lat long start, time, date, everything like that. So a pretty interesting data set to work with, but when we think about how could you visualize that, or how could I query that, or how could I make it actually really useful, that's a lot of data. And especially when we're talking about geometries and points, we're starting to talk about that at scale, but what if we're talking about billions or trillions of these points and you're storing them and collecting them? What do you do with that? And that's, how can we actually use that to answer these critical questions? That's sort of the next phase in the process. How do we use this to identify retail sales and find locations for new stores using data about who's buying what in which locations, or maybe what customers are going to those locations, or how many visits are coming to those locations? What about if you're a telco and you want to analyze your coverage and your towers and the population and maybe your store footprint to figure out how you should optimize coverage or roll out 5G? That's another common use case that we're starting to see. What about if you're a consumer packaged goods company and you want to align your products to consumers in different points of sale using geospatial data, kind of in the similar flow of a retail case, who's going to these points of sale? Where do they live? Can I plan marketing campaigns to reach them? Where are they? That's something that's pretty common as well. And then a final one I think that is starting to really expand is asking questions about environmental data used for sustainability development and resilient decision making. And of course, this is all tied to lots of different Earth observation data as well as climatology data that is, of course, very large in scale. So this is a map you're seeing here of a project we've been producing for many years called the Global Forest Watch, using data outputted from Google Earth Engine, looking at forestry cover and actually understanding where are areas deforested, how does that intersect with different protected areas, animal species, things like that. Now, here's the tricky part. Traditionally, this location data has kind of been siloed away. So if you know about geospatial systems, they kind of have, in the course of history, had their own data structures, databases. They've had, different databases for demographic data and this other data to enrich with. They've had data for your own data. There's also these things called tiling services to actually visualize the map. What about your raster imagery or DEM elevation profiles? So you start to see that there's this other kind of world of data structures that's completely separate from everything else you're working on. And they don't connect to your other data architecture, right? If you're using maybe a data warehouse or a database or a Spark system like Databricks, which we just heard about, how do you actually get those two to talk? It's traditionally been very difficult. So you kind of have other very valuable data locked away. On the flip side of that, you probably have some location data in these databases or data warehouses you might not be making use of. So how do you bring those two things together? Now, when we talk about cloud native, this is a very general high level about what we define as cloud native, is that it's taking full advantage of the cloud computing model. You have less to worry about in terms of infrastructure and scalability. You don't always need to intervene, but you can if you want to. You're always ultimately connected to your data, which is why we see value in the cloud, and that's kind of why we started doing what we did. And when we talk about the data cloud broadly, when we think about data warehouses, lakehouse, and all these cloud native components, there's really a few key things that stand out, which is the scalability in terms of scaling to massive amounts of data, being cost effective in terms of how you actually compute and separate compute and storage. I won't get too much into the weeds on that. And then ultimately, what the really important part here for us is the accessibility with the usage of SQL, specifically spatial SQL functions. So I asked who's worked with spatial SQL before. Has anyone here used a function that starts with st underscore in their work from a SQL database? There we go, I got one. So most of those functions in your data warehouses use that st underscore buffer or intersection, and there's lots of different types of those. It's just an acronym for spatial type, right? So if you go into your data warehouses, you might find this section of geospatial functions that already exist there. And they're in many of the common data warehouses or databases like PostGIS, which is the spatial extension of Postgres. So we ultimately kind of realized that, and I guess it's a little blurred out there, but we realized that people want to run spatial analysis in the cloud, where their data is, not move data around, not use different data architectures, do it where they already put the time and energy of engineering and putting that data in one place. So ultimately, that's what we set out to build, is a connectivity into these data layers, into these data warehouses and databases, a spatial extension or analytics toolbox that actually brings spatial functions into the data warehouse, so you can run these things like geocoding, creating map tiles, which is a visualization concept we'll talk about, spatial data science functions to understand different interactivity with spatial data from things called spatial autocorrelation and different models like that, and do that all in the home of where you're already putting this time and energy into. So the first step is you can easily connect your data warehouse. You don't have to move geospatial data again. And this is, if anyone's worked with geospatial data or file types, this can be really painful. There's a package called GDAL, the Geographic Data Abstraction Library. It's an open source library to translate geospatial file types. I think at last count, there's like 180 plus different file types in geospatial. There's very common ones like shapefile or GeoJSON, which you may have heard of, and very specific ones from different, I think there's a very specific file type for Norway. I don't know why, but they have their own geospatial file type. So, but strangely enough, they do. But all that data is in the same format when it's in your data warehouse. So it's all living there, it's all interconnected, everything is in one place. So you can connect directly to that. All the effort you put into your data engineering workflows and data processes is picked up right by the platform. And then you can run your queries down to these different data providers from the computing engines. You can go to different data providers and connect right back and forth, all with spatial SQL, which is the core connective tissue of all of this. We also are doing some work towards open geospatial interoperability. So we at CARTO build many of our components on open source. Our visualization library leverages DecGL, which is an extension of VisGL, and we can actually contribute quite a bit to that. That allows you to leverage the community and all these different things that are happening there. Our next big initiative we're focusing on is called GeoParquet. So if you're familiar with the Parquet format, there isn't support natively for geospatial data types. And that's one thing we're working on with a large consortium of different folks, because a few different problems here. One is that these data types aren't talking to each other. There's no single format for every single data warehouse. And so we want to create some interoperability there. We want to make sure that can be picked up by the open source community, leveraging that through workflows like GeoPandas and GDAL and all these things that I mentioned, and have one readable file format across all of those. So we've been doing some work there, and in the new world, what we'll be able to do is actually connect and query from any of these data providers, dump your GeoParquet files into these data warehouses and start running right away. So if you're a data provider, if you're sharing data between teams, it makes it a lot easier to connect and work with across teams from that perspective. So it solved what we see as a very big problem in the cloud with geospatial data. The next is using spatial indices, and that is really helping to improve query and visualization performance. Now, if you're not familiar, there are different ways to describe a spatial index. One is actually indexing your data on your database. That's not what I'm talking about today. This is actually using different spatial indices. There's different ones. There's called quad key, H3, and S2. If you've ever been in the back of an Uber and seen a map that opens up when the driver's there and you see those little like hotspot heat maps that look like little hexagons, those are actually H3 cells. And what they are is it's a spatial indexing system that looks at a geometry or a point, assigns it that weird 88FF00 little string that you saw on one of the earlier slides, and it basically assigns that to that hex bin. There's different zoom levels and different things like that. Now, what does that let us do? It's basically there's different spatial reference systems you can see here. On the bottom, going from left to right, we have your polygons. That could be countries, that could be zip codes, that could be FSAs, that could be dissemination areas, anything you want to describe there. The next one is actually those spatial indices, those H3s, which are the hexagons or grids. And then on the next one is the next two, and then the third is sort of your points layer. And those are the different sort of geographic support systems that you can use. So this sort of gives you a visual of what those different ones look like. H3 is in the middle. On the left is quad key, which is sort of, it starts at a hierarchical level of 0, 1, 2, 3 for the entire globe. It subdivides into 4 and 4 and 4, going down to levels 21, I think. And then Uber H3 has this sort of hexagon division system where there's basically, there's 7 children per hexagon. Now the overlap isn't always perfect, but it deals with projection and area much better. So you get the same shape at the poles as you would at the equator, which is not the case with the quad keys. And then S2 is even more complex. I won't get into that, but that's a Google supported system as well. Now, why should you care is sort of the point here. So we have 2 different operations that are happening. We're doing a spatial intersection. We're trying to find the area between these 2 polygons that overlaps and create a new area from that and figure out maybe how many people live in that area. So on the left, we're doing a traditional spatial intersection, combining those 2 geometries. On the right, we've transformed our polygons into these H3 systems. Now we're doing a true spatial join on the left, which basically looks at all the points and vertices in each polygon, calculates what they do, clips them out, and returns a new geometry. On the right, we just look at do a join based on that H3 string. So a string join is going to be much faster than a complete geometry join, which has a lot of advantages, and that takes your query time and performance down quite a bit. And especially when you're dealing with data volumes in the millions and billions and trillions of points or features or polygons, this makes life a lot easier and more responsive. Now, this is your traditional view of what a spatial join might look like. At scale for some of these spatial joins, this is really the only realistic way to do this. We've had joins that might try to run for hours on end, and we've gotten them down to seconds with just going to this new system. And the other thing I think that's really interesting is you can easily take your data if you go into the spatial support system and join it to data providers quite easily. So if they're in that same system, your join is almost automatic. We're talking about seconds. You can see how many people live in an area, overlap, things like that. So going back to those original questions we answer, we're now getting answers much, much faster than before. There's obviously some impact for visualization, so we can create much more readable maps. When you compare left versus right, it's very easy to interpret where there is more or less of something with this spatial support system. And then finally, all of this is living within our CARTO analytics toolbox. So you can use these functions on the data warehouse open source as you start today. So if you want to check this out and you're using one of these data warehouses, you can actually start using that and go from there. So the other thing I think that's really cool is visualization. So because the query response time is so fast, and because we can actually put these geometries client-side, the rendering becomes much faster. So this is actually a 73 gigabyte data set visualized live with H3 tiles. If we reran the query, we get maybe a couple seconds here, and we would get that response back. So if you want it in the app, okay, well, show me, maybe these are our customers, show me where people bought pizza instead of just all our products, or maybe what about between date A and B? These are questions you can start to answer and get these response times very, very quickly on massive scales of data, which in a traditional spatial join just is very, very difficult. So continuing on, we also have kind of a complete toolbox for running spatial analysis. That's all happening in our data warehouse. Like we said, we can actually, well, those tiles that you saw rendered front end, we can actually create and cache them within the data warehouse itself. So we use the data structures in a data warehouse and store map tiles and visualizations. I think this is a couple terabytes of data that we're visualizing and showcasing and rendering from the data warehouse. So you actually use all that compute power that you put in, all the data that's living there, and just create your map tiles and visualizations from there. And then we also have spatial data science functions. So I mentioned things like spatial autocorrelation, getus or ORDG star. There's a few different ones that, if you're familiar, you can check those out. But they do things like where there are outliers or clusters of different activity. What is the sort of the correlation of different features or these different clusters of areas? So this is looking at potentially answering a question for a CPG product rollout. Where are there clusters of populations that I might want to roll out a new product to? I can figure out which points of sale are in that area and then make a point of sale sort of strategy from that. And then there's also a vertical specific functions. So this is a visualization looking at the optimization, finding a great location for a Pizza Hut in Honolulu using demographic data and things like that. We've actually put those for retail verticals. We're adding some for logistics and CPG as well. And then obviously data. So if you have spatial data, you probably want to use other spatial data. We also have our data observatory where you can actually go in and find different data products. So you can actually look here, we have StatCan loaded up as well as some other open source data sets, but there's also premium data providers there as well. And you can actually use them directly through our interface to load up a data set, enrich it. Maybe you want to see how many people live within a kilometer, what are the number of POIs within 2 kilometers of a location. This all happens through the UI. And it's backed effectively by spatial SQL functions, which is that analytical toolbox that I mentioned before. Everything happens there. Everything's using SQL, once again, in the data warehouse. So nothing's leaving your data warehouse from there. So this is just an enrichment workflow that's finishing, and it will show us for our hospitals in New York City, how many people live in the area within sort of a certain distance of that hospital. So, and the last bit is, okay, have all our data, how do we actually show people what's going on? That's our builder toolkit, so you can actually visualize and see what's going on. Those same spatial indices that I mentioned, you can actually visualize them right through the application and see that massive amount of data, and you can actually requery that right below anytime you want to just get that requerying there. Additionally, if not everyone likes to write SQL, I do, but not everyone does. But you can get that same power through the user interface, doing things like point and polygon aggregations, creating buffers, finding centroids, finding different spatial clusters like dbScan and things like that. We're creating those through this workflow, as well as adding geocoding or routing and all these different components. And then finally publishing and sharing this. So this is a map that shows different fire risk in California and different seasonality, as well as the burned area and sort of that overlap. So you can actually filter this map, see what's going on, and publish that and share that internally or with other groups that you might want. And like I said, we also have some industry-specific solutions. The two we have that have been rolling out are for retail and out-of-home advertising. So this is our retail solution. It's more of what you would call sort of like a site selection toolkit that allows you to actually go in, look at your current stores, revenue, intersect with other data. Actually, if you're very much out of the analytics side, you can actually push that same work you're doing in with your builder and your toolkit into a tool like this and actually showcase it there. So it makes it much easier for someone in that planning phase to do that. So how are people doing this? How are we using this? There's two stories I was going to highlight very quickly here. The first is from TELUS. So they have been working with CARTO to bring in their coverage data. Now, if you're familiar with, has anyone worked with GIS raster data? No. So GIS raster data is effectively interpreted data of imagery of the Earth or other data sets. And it's pretty efficient, or it had been efficient, for storing really massive data. So you might have a DEM, or digital elevation model of, let's say, Alberta. And you might have each pixel represents a physical space on the Earth, maybe 30 meters, 10 meters, 3 meters. And that, when you extrapolate that out, you might have hundreds of millions of pixels that each represent a value. So this is, GIS system, you load this up, you can visualize it, you can remodel it and things like that. That's great. But if your data is constantly changing, you're now managing a file system of hundreds of giant, gigabyte-size images on some place, which becomes quite tenuous to use. So what we've done is actually, how do we bring that into a cloud-integrated system to make that visual and share that across the organization, and also queryable, so we can actually ask questions of that data to say, for a specific tower, what's our average minimum max coverage, how many people live in that area, and what's the overlap of area versus population that I serve. So we're answering some pretty important questions from that. And we actually use that same spatial indexing system to split out the rasters. So it actually expanded the number of rows of that data. So it actually went from like hundreds of millions to almost like billions of data rows. So each little grid is subdivided into a set of hexagons, but the query time improved, I think, about 90%. So instead of asking questions in minutes, you're now getting them in under seconds. So that's a very rapid improvement there from that side. So this is kind of a view of their coverage data, how we're integrating that, visualizing it all from those raster data, but this is in the cloud. It's shareable across the organization. Anyone can go in here and ask specific questions that they want to and grow from there. And the last one is Hawaii DOT. So that's the Department of Transportation, Hawaii. They're looking at using all of this rich data that they're producing within their departments and agencies, but to answer questions about sustainable and resilient development. Hawaii has lots of issues with sea level rise, inland flooding, erosion that they're looking at. So they want to say, where should we prioritize that? How does it intersect with topics around job access? What about equity? How does this provide for different access for our tourism within the space? So they can all use CARTO to, once again, use a single spatial support system, query that data, intersect it very easily across almost 100 different data sets that we're pulling in, and then ask questions about where is our investment risk, where should we be focusing on, how do we improve that, and then also tell that story to stakeholders in the community, to politicians, to the federal government, to say, here's why we should be investing in these projects. So that's a little bit about what we do. Just want to say thank you. I know it's late, I'm the last talker of the day, but thanks for sticking with me. If you want to reach out, there's my email, and you can find me on LinkedIn as well. So, good.
Thank you. Only one quick question from our studio audience out there. How accessible, and I was wondering, how accessible is this for if you're not non-technical? Like, you don't sit around write SQL at night like you.
Yeah. So if you're not technical, that kind of falls in our builder platform. So like I said, you can actually go in, you can load data, you can do those point and polygon intersections, you can create buffers, you can do enrichment. All of that's doable for the interface. So if you want to actually go in and start playing around with that, you can sign up for a trial and start doing that today. There's drag and drop imports. So our goal is to bring more and more and more of that and make it really accessible for anyone who wants to use it. If you want to get in the weeds and get technical, it's right there for you as well. So.
Fabulous. And a lot of this is publicly available, like a lot of the open source data in this.
Yeah, I mean, a lot of our technology, like I said, is built on open source. So we've been kind of committed to that from the beginning. We want to be open source from a technology, from a data perspective. We have premium data if you want to go that route, but we do bring a lot of open data that you can actually go in, like I said, start using today. You can access a free subscription and start using, just get started right away.
Cool. So, and you're around? For people come chat with you?
Yeah.
You're going to hang around, have drinks?
I will.
Fabulous.